Well, hey everyone, thanks for coming. Really appreciate the time today. Yeah, I'm James. I'm a core maintainer for Dask, and I'm also an engineer at Coiled. So wanted to go ahead and I'll set a timer actually, so I know good to go. Let's go ahead and get started. Um, so my guess is this is mostly sort of shared understanding, but I'll kind of set the table just to start. So yeah, Dask is a Python library for scalable and parallel computing. It's a pretty broad project. It covers a lot. It has a lot of surface area, so it covers lots of use cases, like sort of simple but really common sort of for loop style code. If you're working with tabular data, doing ETL pipelines, things like that, we have a data frame implementation that scales that. We also just do sort of arbitrarily custom complex systems, like things get a little hairy in the ML space, and we handle that well. I think this audience, mostly what you care about is array computing, how Dask scales in-dimensional array computations. Actually, maybe not even Dask itself, but actually Dask through its integration with Xarray. Um, so Xarray and lets you sort of lets users have kind of a familiar, simple API that sort of fits their brain well. And when you need to scale to larger than memory data sets, things that like don't necessarily fit on your laptop, Xarray with the same API can hand things off to Dask. Then Dask will then dispatch that computation to a large cluster you have deployed wherever it's deployed, Kubernetes cluster, HPC system on the cloud, whatever the case may be for you, to really just with the same exact user code expand to these large, huge, massive data sets. And that really helps you unlock sort of science at a much larger scale than was accessible before. So this works great. I wish this was the end of the story. I wish we could like it was happy and we could all just go home, I guess. But it's not necessarily the case. It works really well up until about a terabyte. Beyond that scale, the Dask, Xarray, and Friends PyData GeoStack kind of start struggling and breaking down a little bit. It requires a decent amount of expertise and kind of understanding of what's going on under the hood in these libraries, and finagling and tweaking of things to get it to work well at terabyte plus scales. And this is frustrating for everyone. This is frustrating for users and developers alike. So we would like to improve the situation, like improve this whole tool set to work smoothly and robustly up to the 100 terabyte scale. We think that would unlock, that would reduce a lot of frustration first off, and also unlock a lot of use cases that folks are currently sort of struggling with. And we want to do that. We think a key component of that is actually having a solid geospatial benchmark suite. Why do we think that? Because we've done this before, not in the array space, but in the tabular data frame space. So Dask data frame previously had sort of similar-ish scaling issues that we see on the array side. But in the ETL data frame space, there actually already exists a few suites of sort of existing standard benchmarks for those industries. Things that like work with large data sets and cover the main operation folks care about in kind of an end-to-end way that are pretty realistic. And armed with this benchmark suite, specifically, we looked at the TPCH benchmark. We were able to make some serious improvements to Dask. It depends a little bit on the workflow that the actual computation you're at hand, but we're talking orders of magnitude. Sometimes multiple orders of magnitude performance improvements with no user code changes at all, just with refactoring and changing how Dask works internally. And having that benchmark suite was really key because it enabled us to sort of make changes with more confidence. Once you start dealing with these distributed systems, and it's really multiple systems kind of interacting with one another, things get complicated, and it can be really hard to develop an intuition as to sort of just in general what to expect with performance, and also even where is the problem? Like, where's the main problem? Where should we sort of allocate resources to? For example, here's a GitHub comment from this is some PR in Dask to make a change in Dask data frame. And we see that these TPCH queries with this particular change, there was like a huge, significant increase in decrease, improvement in the runtime. But that was also coupled with an increase in memory consumption. It turned out in this particular, so like things are complicated, I guess is the main point here. Turns out in this case, the actual memory used was really small. So if you double it, it's also still small. So it wasn't a big deal, and we moved forward. But having being able to do things in a sort of a data-driven way is really key to making progress in these complicated systems. So we, based on that experience, we wanted to our knowledge, the like existing, the equivalent benchmark suite in the geospatial space does not exist today. So we want to help build one. And based on our previous experience, we found that writing benchmarks is hard, first off. There's a lot of subtleties involved and things like that. So we think that a good benchmark should be relatively simple. We don't want benchmarks to be like the customized person who is the expert and knows the exact incarnation or incantation of like magic keyword arguments to work in this one particular edge case. We want sort of the standard naive user code that most folks would write. We want it to be simple, but we also don't want to sacrifice fidelity of like the actual workflow at hand. We want it to still be realistic. We also think benchmark suite should be comprehensive and cover the space pretty well. We don't want to focus on 2 or 3, niche, computations that only a couple individuals care about. We want to focus on like broad problems that impact lots of groups. We want things to also be moderately independent. We don't want to have a bunch of workflows that are all really just kind of actually testing the same thing. We want to have each one sort of stand on its own. And last but not least, we want these things to be big, right? We care about scale here. We want to focus on the terabyte, tens of terabytes, hundreds of terabytes scale, where folks are actually today experiencing pain. We want to focus on that range. Just to be clear, the Dask developers are not geospatial experts by any means. So we can't actually make this ourselves. We need help from the community and other folks who are experts here. So we put out a call for geospatial, we put out a call for benchmarks here. So I'm linking in the bottom to the GitHub discussion where we were soliciting workflows from folks. And I was really pleasantly surprised to see all the like engagement we got from lots of folks here. And through that engagement, we were able to identify a handful, actually several common workflows that lots of different people cared about. And so going through those common workflows we've identified, the first is rechunking. So in particular, sort of pathological cases where the data layout is like, spatially optimized, but the particular computation you're running, you need to be time optimized. That like all-to-all rechunking is really bad today. Or was really bad, I should say. So yeah, rechunking is the first workflow. The second one that came up several times was computing climatologies. And also just working with legacy data in general, or data formats, I should say. NetCDF came up a bunch, but today if you use Xarray to try to work with the data set that's like 10,000 NetCDF files, you're going to have a bad time. It's not going to be a smooth experience. Atmospheric circulation was another workflow that came up, and regridding and reprojection came up several times. So people really cared about this particular operation. Satellite image processing came up several times, working with stat catalogs, things like that. And then last, geophysical inversions came up as well. So using these workflow ideas, also data sets folks pointed us to public data sets. I want to shout out the like ERA5 hosted on GCP by Google. Thank you for doing that. That's been very useful. But yeah, data sets and actual just code, runnable code that people have that they handed off to us. We're able to put together a few of these benchmarks already. So we've implemented several of these workflows in a public GitHub repo. So if you go on GitHub, the Coiled benchmarks repo, you'll find all these benchmarks here. To be clear, most of them break. We're kind of reflects the current state of things. They break it to larger scales. That reflects, yeah, just the current status quo. The good news is that we've been able to identify through running these benchmarks several sort of common themes and technical work necessary to make these benchmarks run smoothly. In particular, some of these may look familiar to folks here too. Better handling of large task graphs. As you get up to these, tens and hundreds of terabyte scale, the task graph associated with the computation becomes really large and just like totally unwieldy. You have a really bad time, really bad experience with these task graphs. It also became clear we needed to re-implement some of the core methods used here. So for example, things like Xarray's OpenMF dataset, rolling operations in Xarray is another thing that comes to mind. We need to re-implement some of those to be, when using Dask, just more sort of Dask native, more performant. Better hinting at hardware failures. Today, if you run out of memory or disk space, you get a not super informative error. We need to improve that situation to make it easier for users to know what's going on and hopefully figure out a way to help themselves. Also today, lots of time and care is spent sort of right-sizing the clusters, making sure the clusters are the right size to handle the appropriate computation. So yeah, we need to have just better and more aggressive auto scaling, I think. That way, less time needs to be spent on sort of making sure you have exactly the right number of workers, the right number of memory, and changing Dask so that it has more reliable auto scaling and can scale up and down as needed in a way that's reliable for users. Like I said before, at these larger scales, there's certain magic incantations of keyword arguments that get used at different times. It'd be nice to update things such that those were the default values. We had same defaults for all these various, knobs one can turn in Xarray and Dask. And then last, but certainly not least, less reliance on manual overchunking. Today, users at this scale really need to think about how their data is laid out. And it's annoying and error prone and frustrating. So we would like to make Xarray and Dask smarter here and handle all different types of even horrible rechunking data layouts for the particular problem, handle that all automatically for users. So they don't really have to think about their data layout. They can just point Dask and Xarray to their data, things just work. So yeah, I'll finish up by saying, well, first, thank you to everyone who has already engaged in this effort. Again, like I said, the Dask developers would not be able to do this by ourselves. So we highly appreciate and value the support we've gotten from lots of folks here. But feedback is still very welcome. We have pretty strong confidence in the current benchmarks we're implementing and working on. But are there other things that we're missing? Do we have some blind spots here? Are there other key workloads that are important to lots of groups? If you have any feedback on the benchmarks or would like to propose a new benchmark even, please engage on the GitHub discussion. We'd love to have you there. Last, I'll just say thanks everyone here for the time. Really appreciate it. Happy to use whatever time we have left for questions.
There is one question here if you want to answer it
Great.
quick. Are you thinking of adding another aspect of where Dask is deployed as a part of a benchmark results, Coiled versus Ktus versus Ray versus, oh, sorry, I don't know these words.
Yeah, no problem. Kubernetes or Ray or whatever, yeah. So all these benchmarks today are run on Coiled, but that's actually, it's Coiled here isn't important for the actual, it's just the thing that's easiest for us to run on. This could be on Dask Cloud Provider or Dask Kubernetes or some other system as well. Hopefully that gets at the question.
Cool. Awesome. Well, thank you so much, James.
Yeah, of course. Thanks for having me. Thanks, everyone.